So next we have Rohan Naidu. He's probably going to tell us why reionization is caused by these massive galaxies, high redshift. Rohan, go ahead.
Can you see my screen?
Yep, perfect.
And can you hear me?
Yep.
Awesome, perfect. My name is Rohan Naidu. I'm a graduate student at Harvard University, advised by Charlie Conroy. I wrote my undergrad thesis with Pascal Ush, and I have the great privilege to work with this delightful band of people. I'm very excited to share some results with you today that we put out a few months ago about an updated picture of reionization. So I know I'm preaching to the choir here, but even to the true believers, there's never a wrong time to show Avi's beautiful reionization graphic. Two of the conventional pieces of wisdom that at least I was taught as an undergrad a couple of years ago was that reionization is largely done by redshift 6, and it's mainly driven by faint star-forming galaxies that are the leading candidates of reionization. But in the last few years, we've had so many really exciting developments. We've finished the first census of galaxies out to redshift 10. We have all these exciting constraints on the IGM reionization history from all these really cool quasars and high redshift Lyman alpha emitters. Tau keeps getting more and more precise with every passing year. We have all these beautiful Lyman continuum measurements, some of which Laura just showed. And we also have tons of reionization simulations that really build intuition as to what's going on and which galaxies are reionizing the universe. So in this work, what we have tried to do is really unite all these developments self-consistently, bring them all together under the same umbrella, and see what they tell us about reionization. So our umbrella of choice is a very simple empirical model that Sandro Takela built out. The very simple assumption in this model is the star formation rate and growth of galaxies is intertwined with the growth of their dark matter halos. That is the very simple bedrock of this model. And these halos are seeded with this redshift independent star formation efficiency that's calibrated at a redshift of 4. And from there onwards, everything else is predicted. For reionization, of course, we're so it reproduces a lot of key observables that we care about in the high redshift community, stuff like luminosity functions, ρSFR, and stuff. In the reionization game, we always focus on these 3 key players: the star formation density, the ionizing photon production efficiency, and the escape fraction. How many of these ionizing photons are actually making it out into the intergalactic medium to reionize them? One thing I'd like you to pay attention to is in this particular figure of the evolution of ρSFR, our model really very naturally reproduces this sharp drop in the star formation density at high redshifts, and that'll become important in a second. The psi ion is consistent with what we think are the best observations that we currently have. And as the escape fraction is a key unknown. So the idea is to keep all this other stuff fixed and let F escape float and see what we learn from all these latest constraints. So to cut to the chase, we find an escape fraction of about 20-ish% is what all these constraints together, along with the constraints from our empirical model itself. Remember, we let the halos evolve after tuning only that star formation efficiency. So everything else is a self-consistent prediction from the model. So we get out this escape fraction of 20-ish%. The most constraining constraints turn out to be the Lyman alpha damping wing, the quasar damping wing, and the requirement that reionization is mostly done by around redshift of 5.9-ish. The reionization picture that is suggested by all this is a really rapid reionization. So you go from the universe being almost completely neutral at redshift 8-ish to being completely reionized by redshift 6-ish, right? So that's only about 300 mega years. There are about there are 5 solar mass B-type stars whose age is about 300 megayears, the time they spend on the main sequence lifetime, to just give you a sense of how rapid we're talking about. And since we put out this paper, there's just been more and more growing evidence that reionization really is indeed super rapid. There's new constraints from the KSZ effect. There's new constraints from the Lyman beta fractions that Ginny showed yesterday. There's more redshift 7 quasars that also suggest this. And while reionization is late, remember that it's still patchy. So you still have certain sightlines along which you're fairly transparent. So is this 20% escape fraction, the one single parameter that we really move around in our simple model, is this 20% average escape fraction a reasonable number? And it seems that the emerging picture really in the last few years really is that around redshift 2, 3, you can really get up to about 10-ish%. So the question then that we really wanted to answer with our model was, how do you go from basically 0% escape fractions in the local universe to about 10% at redshift 3, and then 20% at these higher redshifts in a very self-consistent manner? So one solution that suggested itself just by looking at these Lyman continuum leaking detections is that most of them tend to be really, really compact and have very high star formation surface density. So the amount of star formation being compressed in a very small area. And there's also a lot of motivation from this new generation of reionization simulations that the way you get to high escape fractions is by really carving out channels in the ISM through feedback on very small scales. So just by linking the escape fraction to star formation surface density, we once again throw this whole kitchen sink of constraints against our model and see what falls out. What falls out is a fairly similar, really rapid reionization history, but the ionizing budget is very different. The galaxies that are doing the bulk of reionization are actually a very small handful. So here I'm plotting how sigma is changing as a function of stellar mass at redshift 7 that we believe is the heart of reionization. And you see the escape fractions are really being driven by these very compact galaxies at masses of mostly greater than 10 power 8. So the picture that falls out of this is that about 80% of the reionization budget is controlled by really this small handful of galaxies. You see, so these galaxies are dominating reionization, but they're very, very rare compared to the bulk of the population. So this is a highly unequal society. It's a society of a very high Gini coefficient. The reionization budget is not equally distributed. And these kind of very compact high sigma galaxies become more and more common towards higher redshifts. So it very neatly explains why you get a small escape fraction at around redshift of 0, which grows towards higher redshifts. So then what about the conventional picture? The conventional picture of, this massive reservoir of very faint galaxies that are super abundant doing the bulk of reionization. So I show one such model here, which is super helpful to think about this problem, right? Where the escape fraction goes inversely to the halo mass, Finkelstein 2019, where the reionization that you get is much more smooth and starts very early, right? Which these constraints and the other constraints that I outlined seem to disfavor. And I've tried to summarize this, this picture in this cartoon where if you have these very faint galaxies contribute too much too early, you end up reionizing the universe very early. So we've done a very brave thing here, right? We're saying the bright galaxies are doing all this work. Bright galaxies that are currently observable, MUV less than -18 galaxies. So there's tons of tests that one can look at to figure out whether this hypothesis holds or not. One interesting simulation that recently came out from Fire2, and I think Shengcheng is going to talk more about it, really supports the same picture of, the escape fraction here as a function of stellar mass really seems to favor more massive galaxies, especially in the higher resolution simulations. Another simple test is a very direct one. We're constructing these stacks of redshift 2 to 3 Lyman continuum leakers. You just stack the high sigma ones, and you see that the detection really is in the high sigma sources compared to the lower sigma ones. Another test is just by directly looking for the oligarchs at very high redshifts, right? And we've heard a lot about COLA1 and some of these other double peak Lyman alpha emitters that are likely like powering their own bubbles without any assistance from like some of these fainter galaxies around them. Another less glamorous thing to do, but something that I really encourage the community to do would be to focus at lower redshifts, but try to get very resolved Lyman alpha profiles along with systemic redshifts that can help us discern whether they really are leaking with high escape fractions. The Alpine survey has a very promising result on this front, where they show that the Lyman alpha offset compared to the systemic seems to really be going down as you go to higher and higher redshifts, but you need high resolution data to really confirm that. Similarly, we are leading, Charlotte Mason is leading this wonderful survey at the CFA, where we are trying to get these super high resolution Lyman alpha profiles to figure out what's going on. Then there's tons of other tests with upcoming facilities. 21 centimeter maps should really nail this. Absorption line spectroscopy would be very helpful as well by getting the covering fractions. Very happy to hear your ideas. And I'll end with this summary. Thank you so much for listening to me. And it's really been a privilege to be part of this conference, hanging out on the chat with so many of my idols and people that I look up to. So thank you so much for this opportunity. I'll take questions.
All right. Yeah, thank you, Rohan. So they have some questions on the Slack already. The first question is there a way you can quantify the degeneracy between the F-escape constraints you get and other parameters, for example, the average faint end slope of the luminosity function in the problem?
Right, so in this particular model, of course, the only thing we are varying, the only like free parameter we are leaving is the escape fraction. But this plot does cast some light on how that degeneracy might work, where when you truncate at lower and lower MUV, you need to ensure you don't reionize too much of the universe too early. So here I'm just like, doing a theoretical kind of calculation where I just assume some faint end slopes, a very like reasonable set of parameters, and see what falls out in the same space with these same constraints. And I expect the space to shrink even more once we add the new constraints I talked about earlier.
All right, thanks. The next question is, what faint end slope do you get from a UV luminosity function anyway? Is that comparable with recent observations?
So the model predicts faint end slopes that really are very much in line with the observations, right? So here is the redshift 6 UVLF. And in purple is shown what our model predicts, and it seems to be in the thick of the data points. Even more formally, just looking at chi-square values, it seems like we're doing okay. The only significant disagreement actually is on the bright end with these points from Atik et al., where we're disagreeing slightly.
Thanks. There's an anonymous question. There are indications that some galaxies have very low escape fraction, for example, from the fast GRB holes, while others have very high escape fraction. What would including this scatter affect your results?
So I'll point out that there is a lot of scatter that just falls out of the model itself, right? Like, so there's a huge diversity in sigma. So I'm not just saying massive galaxies are doing it, right? Like in this model, it's the more massive galaxies that are also very compact and also very star forming that are doing it. So there's a lot of scatter that falls out of sigma itself. As for lower redshifts, when you go to lower and lower redshifts where a lot of these constraints are available, things get more complicated because of stuff like dust. And yeah, so like in our model, at least at redshift 4-ish, 3-ish, where a lot of these new constraints are coming in, we expect escape fractions of about 10-ish% on average. But this is interesting, right? The fraction at F escape greater than 0.2 is really small. So it very much is consistent with this picture of there's a very small fraction of galaxies which have high F escape, and the mean is also low at lower redshifts. This pink line in particular is illustrative.
All right, I have quite time probably for one last question. Does your model with 20% F escape naturally reproduce the flat slope of the background boson ionizing emissivity measurement in redshift 5 to 3?
That's a really cool question. So in the paper, we do show that like we satisfy that. I don't have a plot right away for it, but we have a plot of anion versus Z. And at redshift 4-ish, so remember that our model is really a model for the high redshift universe. So we calibrated at redshift 4 and like let it do what it does for high redshifts. So extrapolating it backwards is tricky, but at least at the higher redshifts, it does seem to match the constraints from Bolton.